Okay, so hello everyone, welcome to BVLSI lecture number 28, which we are conducting in the online mode. And today's topic will be N channel enhancement MOSFET operation. N channel enhancement MOSFET. How does it operate? We'll study. Okay, we'll study only the conceptual part today. Alright, so first of all, let us draw the structure of the MOSFET. So MOSFET consists of, first of all, metal layer. So this is my metal layer M. This is normally aluminum. On top of it we have oxide layer. Here it is my oxide layer, and here we have N plus source and N plus drain diffusion layers, diffusion junctions, and then bottom we have P silicon substrate. So this is P silicon substrate. Okay, now let me mark the connections. So this is metal, this is my gate terminal. Okay, this is my source terminal, I'm writing in short form as S, and this is my drain terminal. Body terminal, normally in model integrated circuits, body terminal is not taken from bottom. This is the body actually, but it's taken from above. So this we call it as a small N plus layer over here, and we call this packet as body. Now unless specified, body and source terminal are always connected together, and they are with respect to ground. So all the voltages VG, S, VD, S are with respect to source, which is grounded. Okay, is this thing clear? So this is my oxide layer. So this is oxide. This is metal, which is normally aluminum metal. Okay, and that is my P silicon substrate. Understood? So you can draw this MOSFET structure, or you can just wait for the explanation. So we have to basically, I have to basically explain you how the output characteristics looks like. Okay, how the every curve has come, and also then transfer characteristics is the derived characteristics from output. So that's fine. All right, can we start? Okay. Okay, some student have joined. Let me admit. Okay. Yeah, let us continue. So this is my N channel MOSFET structure. The distance between the source region and the drain region is my channel region. So this is my channel actually. Let me mark it over here. So this is L, channel length L. So L is my channel length, and yesterday I have showed you the width also, channel width. Okay, so let us study its operation. So first of all, let me draw the output characteristics. So output characteristics of the MOSFET is between VDS and ID. Okay, correct. Now what is the condition for this MOSFET to form the channel? What is the condition? The condition is, anyone remembers the condition? For N channel to form, what is the condition? VGS should be greater than the threshold voltage VTO, where VTO is the threshold voltage. Agree? And we have seen the expression of the threshold voltage, what all things it contains. So if I say if VGS is less than VTO, can I say a channel is formed or no? So if the gate to source voltage is less than VTO, no channel is formed. Okay, so let us say we have applied the VGS voltage, and the VGS voltage is such that VTO voltage, let's assume that it is around 1 volt, and we have applied VGS around, let's say this time it's around 0.5 volt. Okay, now even if we applied a value of VDS, now VDS is like this, we have connected VDS like this, see, even if I apply some value of VDS over here, voltage, let's say VDS is 1 volt or 0.5 volt, will this device conduct, and where will be the characteristics? Can you tell me? Will there be any current in the circuit? Yes or no? Tell me. Can any current flow? Yes? No?
No.
Okay. Can you tell me, due to VGS, which electric field is present? Due to VGS, which electric field is present? No. EY.
EY.
EY is due to VGS and EX is due to VDS. So now, since no channel is formed, what is the condition we are in? Depletion condition. Why? Because we are applying positive voltage to the gate terminal, okay, and we have applied negative voltage to the source terminal. So basically, when we apply positive voltage over here, the holes will be attracted towards the negative part of the supply, okay, towards the body terminal. So what will happen is, these holes which are over here will be attracted, will be moving away from the surface, so they leave behind the immobile ions. So these are the immobile ions which are there present. Let me do it. This depletion layer. So depletion layer will be formed, so filled with the immobile ions, okay. So no way there is no channel formed, so N plus source and N plus drain is isolated by this depletion layer. So this is my depletion layer which is present. Remember, depletion layer doesn't go anywhere, so this is a depletion layer charge. So these are depletion charges, immobile charges, they will not contribute to current flow. So in this case, my channel is not formed, so no channel is formed, this condition is satisfied, no N channel is formed. So even if I apply any gate voltage, drain, we apply positive voltage with respect to source terminal, no current can flow in the device. So where is my ID point? ID point is over here. Did you get it? ID point is in the 0 0. So VDS also we have not applied. Even if we apply, you will get a 0 only. So even if you apply over here, you will get it here only, 0. So we are at 0 0 point. We have not applied any VDS. Even if you are applying VGS, still the current will be 0. Okay. So what is preventing the current to flow? So here what are we doing? We are applying VGS equal to 1 volt, VTO is equal to 0.5. So this condition is satisfied, no channel is formed, and ID is 0. So in this case, ID is 0 microamperes. Okay, this is normally in microamperes and VDS is normally in volts. So we are in the, which mode of operation is this? Can you tell me? Of MOSFET? Cutoff mode, correct? So MOSFET is in cutoff mode right now. Okay? Yes, everyone? Any doubt over here? So drain current is 0 since source and drain regions are isolated by the depletion region. Okay? So this depletion region charge density, do you remember in your threshold voltage, what is the depletion region charge density over here? QBO. So because of this depletion region charge density, will prevent any current to flow. Okay? So in this case, the device is off. So what is my ID off here? Current is 0. So in such a scenario where VGS is less than VTO, even if we apply the value of VDS, still the current will be 0. So ID off will be for the condition VGS less than VTO. So this condition you should note it down. Sometimes they ask in the numerical whether in which operating mode device is operating. So your device is operating in cutoff mode today, right now, in this situation. Agree? Everyone?
Yes, sir.
Okay. So this was case number 1. Now let's start with case number 2. Let me draw. I'll keep on drawing the same thing again and again because it's important to understand that we need to remember the structure. So case 2 is, I'll make VGS greater than VTO. Okay. But I'll make the source terminal 0 and drain terminal also 0. So basically I will make VDS equal to 0. So let's see in which operating mode the device is, whether it's in cutoff or any other mode of operation. So let us quickly draw the structure. So how the structure is? Again, metal, oxide, semiconductor. So this is metal, this is my oxide layer, and I'll keep on drawing again and again until it becomes habitual to you to draw the MOSFET structure, because very important. So this is my MOSFET, P silicon substrate, okay, and here I have a small packet of P plus. Now let me draw the terminals again. This is the source terminal, this is the body terminal. Source and body are connected together for N channel. This is my gate terminal and this is my drain terminal. So what are the conditions? We have applied VGS, which is greater than VTO. How much was VTO? 1 volt. So let's say VGS we have applied is 1.5 volt. So we have applied 1.5 volt and VDS is 0. So that means this terminal is grounded still. Okay. So drain terminal is grounded. Gate terminal to source terminal we have applied VGS equal to 1.5. Now tell me what will happen. VGS is greater than VTO. So is the device, if the channel formed, yes or no? Is the N channel formed?
Yes, sir.
N channel is formed since VGS okay, N channel is formed since VGS is greater than VTO. N channel means inversion layer. So sufficient number of minority charge carriers are deposited over here because of application of electric field. Now what is the electric field? Because of which electric field the carriers are getting attracted? EY. So EY is due to VGS. So because of the influence of this electric field, the minority carrier electrons which are there are forming a N channel this way. Okay, so this forms the N channel. So this is my N channel is formed. But drain voltage is 0, source voltage is also 0. Will there be any current flow? So N channel is formed, but will there be any current flow? Tell me. Hello. The N channel is capable of carrying the current, but there is no phase difference, there is no voltage difference between drain and source, so no current will flow in the circuit. Okay, in spite of channel being formed. Now I'll tell you in the different way. The charge which is present over here because of minority charge carrier is called as QI, inversion charge. This is inversion charge, inversion layer charge. Okay, that means it is density of mobile electrons in the N channel. So for the current to flow, we should apply VDS difference. VDS should be applied. Because we have not applied over here. Okay. So what are the reason for the ID not flowing over here? Let's say VGS voltage is 1.5 volt. Yes or no? Now, can you tell me here if I apply 1.5 volt, how are the charges distributed? Can you tell me? So here it is positive. And here there are negative charge, right? This is negative. So this difference voltage between gate and the channel. See, voltage between gate and the channel is this. This is the gate, this is the channel. So I'm calling about VGC. Can you tell me throughout the N channel, how much is VGC? Throughout the N channel, how much is VGC? Here it is 0 and gate voltage is 1.5. So how much is VGC? 1.5 volt throughout. Okay, so the potential difference between gate and the channel is 1.5 volt throughout the length of the channel. So we know what is Q is CV, yes or no? So in this case, what is QI? Inversion layer charge. What is QI given by Cox into VGC? Yes or no? Yeah, so Cox is fixed because Tox is fixed. Yes or no? So now we know, we have seen that VGS is also fixed, right? VGS is same throughout channel. So through N channel it is same. So that means QI is fixed, right? Now for the current to flow, what is the drain current given by any current given by dq by dt, right? So here it will be dqi divided by dt. Derivative of a constant is what? Can you tell me? What is derivative of a constant?
0.
That's your answer. So since the gate to channel voltage is uniformly distributed across the n channel, current will be 0. So this is the way, in spite of channel being formed between source and drain terminal, no current flow exists in the device. Device is capable of carrying current. Okay, and the shape of the n channel is uniform throughout, but device does not conduct any current flow, right? So your characteristics will be VDS versus ID. Still it is over here, still the point is over here. Here again ID of is 0. So device is in which mode of operation here? Cut-off mode of operation. Again, in spite of VGS being greater than VT. Why? Because here VDS is 0. Okay, VGS is how much? 1.1 volt. VGS is VGS is 1.5. VTO is 1 volt. Still, this is what happens. Okay, understood? So in this case, in spite of VGS greater than VTO, still the current is 0 because of this. Drain to source voltage is 0. Because of only that reason, your current is 0 still. Understood this point? Can I move on to the next point? This is case number 2. Hello students, can I start with the next one?
Yes, sir.
You all are following or no? Tell me this. Are you able to follow?
Yes, sir.
Okay, fine. Next.
Yes, sir.
Next. We'll go to case number 3. Slowly and steadily we are moving ahead now. Case 3. So case 3 is VGS is greater than VTO. So N channel will be formed and VDS is very small applied. VGS is greater than 0 but a small value. Maybe around, let's say that value is very small, 0.1 volt. Okay, so now let us draw the device again quickly. So this is my gate terminal, this is my oxide layer, and this is my N channel which is formed. This is N plus source, N plus drain. I am repeating the drawing again so that it becomes part of your system. And this is P plus. Let me mark the terminals. This is body terminal. This is my source terminal, gate terminal, and drain terminal. Now source and body are connected together, right? Now we apply the voltage between gate to source, VGS. How much did we consider? Let's say VTO is, let's say for the example sake, VTO is 0.5. We have considered 1 volt, so we'll consider 1 volt only. 1 volt. VGS is how much? 1.5, and VDS is how much? 0.1. So this is 1.5, and we have another voltage supply, VDS. VDS is 0.1, very small. Okay, will there be a channel formed over here? Okay, so believe me, there will be one more thing which is forming. Tell me. So if I go back to the structure, this structure, where is the depletion layer? I have shown only the N channel. Can you tell me where is the depletion layer here? So tell me, this is a P silicon, right? So if I consider this is my PN plus junction, yes or no? This is PN junction, and PN junction we are applying, this is a reverse bias because here for the substrate we are applying a negative voltage, and here we are applying gate positive voltage. So this PN junctions are reverse bias, and that is a formation of a depletion layer. So how do you show a depletion layer over here? Depletion layer, you show it like this. See, like this. This is a depletion layer between P and the here N plus layer. Okay, similarly here also we can show the depletion layer. So channel is formed inside the depletion layer. So the depletion layer will be showed over here like this. Sorry, let me draw it again. Okay, it will be tapered near the channel, and then again we need not show that again and again. This is once I'm only showing depletion layer. Do not ever forget that depletion layer is absent, it's present. Inside that we form a channel. Now because VGS is greater than VTN or VTO, this channel is formed already. Okay, so this channel is formed there only. These are all minority carriers. So this is my N channel formed, but don't forget there is a depletion layer also inside. Okay, this is oxide layer, this is oxide. I should have written that. Okay, now tell me, will the current flow in the device?
Yes.
Okay, fine. Yeah, the answer is yes. Yeah, that's true. The current will flow. In which direction the current will flow, that also we will decide right now. So VGS, here the condition is satisfied. VGS is greater than VTO. So our N channel is formed. Okay, N channel is formed. So N channel is capable of carrying the current. Now when we apply VDS greater than 0, a potential difference exists between drain and source. Okay, so here we are applying positive voltage and here we are applying negative voltage. So it's like, see, this minority carriers are formed due to EY electric field. Now we have a situation that EX electric field is also there. EX. So let me just show you like this. Let's say I have my here, if you can imagine over here, we have N plus drain, N plus source and drain is there, and now we are applying voltage over here 0.1, and here the voltage is 0. Okay, and throughout, this is my length of the channel, this is L. I am just explaining it below, so for simplicity, and this is my N channel which is there formed. Okay, this is my oxide layer is there above, and this is my gate terminal. Just imagine, this is my gate, this is oxide layer, and this is my metal, this is my gate voltage. So in spite of the gate voltage, let's say this is my gate. Okay, this is my N channel. Okay, so can you tell me, I agree, VDS, if you apply around 0.1 volt, current will flow. How will the current flow? How will the electrons get transferred from where to where? Electrons will start from here, N plus source region. It will enter the N channel and it will go reach towards the drain terminal. So how is the current flowing? Current is flowing into the drain terminal and coming out of the source terminal. Yes or no? Conventional current direction is opposite to the flow of current. So electrons flow from source region, source का N plus region to channel, to N channel, and it will reach to drain terminal, which is again N plus. Okay, so your ID will flow from, what can we flow from? Drain to source, whereas your electrons flows from source to drain. Are you understanding this? Yes, no, what? Hello?
Yes, sir.
Okay, fine, absolutely fine. Now we have to concentrate a little more. Now listen here, you know, this is my, I know this is my channel, so let me just mark it separately. Here I am writing something. Now concentrate, please concentrate. We are determining key how will be the characteristics here, VDS versus ID. How will the characteristics look like? Because here we have applied 0.1 volt. So where will be my current and how will be my current flowing? Okay. Now tell me, when I apply VGS, this is 1.5, due to EY electric field, minority charge carriers will be attracted near SI-SiO2 interface. Now as soon as I apply 0.1 volt here, VDS, what is my gate to channel voltage? Tell me. Here, so here there are positive charges, here we with respect to channel. So over here, tell me, over here, what is the gate to channel voltage? Gate voltage is how much? Hello? 1.5, right? Yes or no?
Yes.
And how much is the channel voltage? Matlab source voltage, how much it is? How much voltage is required? This is VGS. See, VGS has to be greater than VTO. Okay, that means VGS minus VTO should be greater than 0 volt. So how much is VGS minus VTO in our case? VGS is 1.5, VTO is 1 volt. So how much is VG? This should be, how much is this? 0.5, right?
0.5.
हाँ, so यहाँ पे है 0.5 volt. समझ में आया? Did you understand this? Gate to channel voltage कैसे आया? Okay, so it should be 0.5. Now over here, see source near the source end it is 0.5, whereas about here, ये देखो मैं बताता हूँ, एक चीज बता रहा हूँ, ठहरो. So if I have 0 volt over here, okay, and this is my source region, this is my drain region, which is 1 volt, 0.1 volt. So this is my channel length L. This is my channel actually, and this is my channel length L. Let's say if I divide it into 3 parts, here midpoint mein, okay. So this 1.1 volt to 0 volt will be distributed along the channel uniformly, right? मतलब यहाँ पे gate to channel is how much? यहाँ पे source end में VGS and VDS there is difference, right? VGS is same throughout, right? See, VGS is same throughout, is same 1.5 volt throughout. And channel form करने के लिए कितना चाहिए? VGS minus VTO should be greater than 0. So around how much? 0.5 volt. That is agree? So how much is VGD? VGD and VGS. VGD कितना होगा? VGS minus VDS. कितना हो गया ये? And for the channel to form, this should be VGS minus VTO minus VDS. So how much is this? 0.5 minus 0.1. At the drain end, how much is the voltage over here now? ये 0.1 है. Here it is 0.5, 0.05. We can say in the mid almost. ये voltage distribute कैसे होगा? 0.1 and the mid of the channel it is 0.01 drain voltage, and here it will become 0, right? So VGD कितना होगा? VGD same as VGS only. How much it is? 0.4, right? Yes or no? Hello? Understanding? Are you understanding how this has come? See why I am writing VGS minus VTO, because that much voltage is required to form the channel. VGS minus VTO voltage is required. So gate to channel voltage over here at the drain end will be how much? Can you tell me? VGC कितना होगा यहाँ पे? 0.4. So somewhere in the middle it will be how much? Just assume. VGC will be how much over here? Somewhere in the middle. But how to say it?
0.45.
हाँ, 0.45. So gate to channel voltage is not uniform. Yes or no? यहाँ पे मतलब charge less है. Less voltage मतलब less charge है. Meaning the channel is slightly tapered. It's not uniform. मतलब अगर same रहता, अगर uniform रहता, if my VGS is uniform, my channel will look like this. If VGC is constant, but VGC is not constant, so what will happen is my channel will be slightly tapered. So this is my source region, this is my drain region. My channel will be slightly tapered over here like this. Because होता क्या है पता है? What is I? dqi by dt. Yes or no? Right, your current is dqi by dt. So qi over here is more, whereas qi over here is less, because q कहाँ पे चला गया voltage? Some voltage is lost in the drain side, So we can see this voltage is point 1 with respect to source. So VGS is VGD over here at the source end is how much? VGC is 0.5. यहाँ पे 0.5 का ड्रॉप है, पर यहाँ पे how much it is 0.4. So here the voltage is 0.5 and here it is 0.4. So obviously this channel will be tapered slightly tapered in the sense it was uniform like this. Now it will become slightly towards this side. This charge will be slightly less compared to this charge because the gate to channel charge is different over here. So here it is gate to channel charge is how much? 0.5. Yes, and here it is how much? 0.4. So that's why the N channel will be slightly tapered. So N channel is slightly tapered at drain end. So मतलब ये still uniform है ना, still the current can flow uniformly, right? देखो पहले channel ऐसे था, this was the N channel first, current can flow uniformly, right? Now it has become slightly tapered, ऐसे बन गया, yes or no? Still the electrons coming over here can still travel from the drain terminal and source terminal, can travel uniformly in response to the voltage VDS, yes or no? So electron can travel very easily. So how will be the current now flow? Can you tell me? Current flow will be uniform, current flow will be uniform. The N channel is tapered still, but the current flow will be linear. So the current will be like this, straight line. Why? Why it will be a straight line? So in response to VDS, you will have a very small current, maybe around 0.1 microamperes. But why it is a straight line? Can you tell me? Hello? Yeah? Why it is a straight line? Because still the channel conductivity is more or less not changed. See, it is around difference between this area. This is 0.5 and let's say this is 0.4. Still it is not that much tapered, right? It is 0.5 over here, 0.4 over here. Still the electrons can easily flow, no problem at all. Yes or no? Yes or no? So over here, as I told you, Qi over here is slightly Qi. Inversion charge over here is slightly more, here it is slightly less, that's it. But still the channel is uniform and the current can flow. Why it is linear is because current can easily flow past through this N channel without any problem, even though the channel is tapered. So ऐसे होगा ना, देखो, I've drawn very proportionality very very small. This is N plus, this is N plus region, and the channel को फर्क भी नहीं पड़ेगा. It's almost like this way, almost become like this, tapered. तो जो इलेक्ट्रॉन्स थे यहाँ पे easily flow हो गए without any problem. The channel will be seen, it's almost uniform. So that's why it's a straight line. समझ में आ रहा है? Hello, are you able to follow?
Yes, sir. Yes, sir.
Okay. Now I increase this voltage from 0.1 to 0.3. Now tell me what will happen if I increase this voltage from 0.1 to 0.3. होगा क्या बताओ? Tell me this. What will happen? Come on.
VGD will decrease and the N channel
VGC.
VGC.
So यहाँ पे कितना होगा अभी? 0.5 माइनस यहाँ पे 0.2 होगा ना? करेक्ट?
हाँ सर, राइट.
0.2 होगा बिकॉज VGC का फॉर्मूला क्या है, VGS minus VTO minus VDS. So at the source, at the drain end क्या होगा इसका वैल्यू, दिस इज 0.5 minus 0.3, so 0.2 होगा, right? Yes or no? Will it be 0.2?
Yes, sir.
And at the source end it will be 0.5 only, right? So VGC at source end will be 0.5 only. So channel will become even more tapered. Yes or no? So अभी ये tapered था, ऐसे था, now it will become more tapered like this. Yes or no? So here the voltage is 0.5 VGC, here it will be 0.2. Let me show that in that slide once. So होगा क्या, what will be happen to this current now? Will the slope of the current change or yes or no? This is a different slope. Now channel conductivity area कम हो गया ना, so conductivity is slightly reduced because less number of this area is reduced now. So what will happen now, यहाँ पे of course QI will be more and here QI inversion charge will be less. So now what will happen, the current will increase. Will the current increase? Yes, because drain to source voltage is increasing, but this curve will be, earlier it was a straight line over here, let's say from point 1 तक straight line था, point 2 तक straight line था. Once it reaches point 3 के बाद point 1 के बाद slope change होगा, so its slope will reduce or increase. point 1 तक इधर ही था, क्या होगा, reduce होगा ना, reduce, yes. So slope will reduce because the area is reduced. Yes or no? Agreeing to this or no?
Yes, sir.
Now let's see one more document. I'll show it to you. Just wait. All this is there. I'm taken from there only. So this is what I was telling you. Here. I hope this is clear to you. So earlier we have taken VDS as here the slightly voltage difference is there. VGS is 1 and VTO is 0.5. So difference is 0.5 only. VDS is 0.1 initially. So here is the tapered channel. Now we applied here 0.3. So 0.3 के लिए यहाँ पे we get 0.2, here we get 0.3 and here we get 0.5, right? Gate to channel voltage. So because of that, channel has tapered here. So for the N channel to exist, VGC should be greater than 0. तो channel exist नहीं करेगा. So VGC is the voltage drop across the gate and the channel region. So at the source end, the channel gate to channel voltage is 0.5. So QI will be maximum at the source end. Yes or no? Are you seeing this? Yes. Here.
Sir.
At the drain end, what is VGC? 1 minus 0.5 minus 0.3. That will be 0.2. So QI is slightly less at the drain end. Okay. So there is less inversion charge at the drain end and more inversion charge at the source end. So what will happen is ID will continue to increase, continue to flow, but with a lower slope. So this region of operation is called as linear region of operation. So ये कौन सा linear operation है? Linear mode of operation, and also it is called as non-saturation, or it is sometimes also called as ohmic, linear mode of operation devices. Okay. So here in this example we have taken VGS as 1.5, VTO as 1 volt and VDS we have given up till 0.3. तो ये कभी तक चैनल रहेगा यहाँ पे? Can you tell me? Can you tell me now? Till where it can channel will be disappearing? As long as VGC is greater than or equal to 0. बराबर है?
Right, sir.
So that means अगर ये condition आया, let's say we have reached this condition. Now here we have taken VGS as 1 volt, so take it as VGS as 1. VTO is 0.5, VDS is 0.5. So now what will happen? Tell me. What is VGC at the drain end?
0.
Yes. 0. Oh, sorry. So it will be VGS minus VTO minus VDS, which is 1 minus 0.5 minus 0.5. जीरो मतलब चैनल होगा क्या यहाँ पे? नो, द चैनल विल बी कंप्लीटली गॉन एट द ड्रेन एंड, यस और नो? एंड ओवर हियर एट द सोर्स एंड कितना होगा यहाँ पे? 0.5. I hope you are following. So VDS is 0.5 over here, but that will be, used up by the N channel, right over here. So N channel will be completely tapered. So what will happen over here is, how will be the N channel over here? N channel will look something like this. So this is my N plus source, N plus drain. So my N channel will be completely disappearing from the drain end. ये देखो यहाँ पे. So over here VGC was 0.5, here it's becoming 0. This is N channel. Okay, so will the current flow still? Yes, current will flow. देखो, actually current will reach the maximum value. यहाँ पे current तो flow होगा, current तो flow हो रहा है. Okay, this is my oxide layer and this is my gate. Sorry. So this is my gate. So this is oxide layer. This is your drain, gate, and this one. Okay, so current will flow, but what will happen now? See, initially it was at 0, then at 0.1 it has gone to some linear value. ये देखो ऐसे हुआ था ना 0.1 में, ऐसे, right? Then 0.3 में क्या हुआ था? What happened at 0.3? Slope change हो गया. तो अभी slope change होगा वापस? Yes, the slope will change and will reach over here. तो ये तीनों पॉइंट मार्क किए मैंने, ये देखो 1, 2, 3 and 4, बराबर है? So this region of operation is called as linear mode or non-saturation. Agreeing or no? So here, what have we applied over here? In our case, we have applied VGS greater than VTO. This is VDS. So very small values of VDS voltages. I have shown very small value. Actually, reality में ये ऐसे ही रहता है, दिखाओ. I have drawn it very big. VDS is from 0 to 10 volts normally. Okay, so ये 1 volt के अंदर ही दिखा रहा हूँ, छोटा सा section दिखा रहा हूँ, देखो. Here I am showing this section. Yes or no? Can you imagine this? I have highlighted this only here, expanded this over here. Okay, so very small region के लिए वो maximum चला जाता है. Now after 0.5 voltage क्या होगा? VDS अगर, what will happen if I give VDS greater than 0.5? What will happen? What do you think will happen?
Then the current ID will almost be constant,
Okay.
irrespective of increasing VDS.
Okay, चलो ठीक है. So what is the condition for this linear mode of operation? So MOSFET is in linear mode of operation. Let's write the condition. So first condition is VGS should be greater than VTO. Agree? What is the second condition? VDS should be less than VGS minus VTO. Agree or no? देखो,
Yes, sir.
अगर ये 1 volt है, if this is 0.5, how much is this? How much is this? 0.5. So अगर VGS less than 0.5 हुआ, then only this linear mode operation exist करेगा ना? Yes or no? So ये less than 0.5 होना चाहिए. So this is the condition for MOSFET to be in the linear region or non-saturation region. ये लिख के रखो कहाँ पे, तो very very important. Very very important. ये boundary है. So here is, till here only we have linear region. Then we have a saturation region coming up next. Okay? Understanding? Students, please let me know if you are following or no. Yes, no?
Yes, sir.
अच्छा, एक बात बताओ ना, conceptual part है. Here almost QI is present, right? QI is more here, I mean constant almost. And here QI is becoming what?
0.
Will it ever become 0? Do you think it's ever become 0? So if yes, under what conditions it will become 0? Tell me. So
When VGC is less than 0.
okay, yeah. So this condition where VGC becomes 0 is called as pinched off, pinch off point, is called as pinch off point. Okay, and this happens at, let's say if this is मेरा ये x equal to 0 है, okay, this is length of the channel x equal to L. Okay, so at x equal to L we get Qi is becoming 0, inversion charge density is becoming 0. So we say Qi becomes 0 at x equal to L. Yes or no? Hello, are you understanding? Yeah. So we say the channel is pinched off. Channel is pinched off at drain terminal. So this condition we call it as region of operation. Here we call it as when Qi becomes 0, we call it as edge of saturation. क्या बोलते हैं? Edge of saturation. Are you understanding? So edge of saturation मतलब ये वाला point. This point is edge of saturation. ये वाला point. Up till here it is lower than that, then is linear region. इसके बाद ये edge of saturation है. What is the condition for edge of saturation? Can you tell me? VGS greater than VTO. और ये क्या रहेगा? Are you following this? Edge of saturation में क्या होता है? Qi becomes 0, right? So VGS is 1 volt. This is 0.5 और ये भी 0.5 है. तो VDS कितना होना चाहिए? 0.5 volt. So this region of operation is called as edge of saturation. Agree?
Yes, sir.
So now what can you tell about the inversion charge? So Qi, which is inversion charge, varies with channel length. ये बहुत इंपॉर्टेंट पॉइंट है. ये देखो again and explain. So this is my channel, this is my source region, this is my drain region. Let me mark some calculations over here. So this is x equal to 0. अगर ये 0 consider करता हूँ तो this is length of the channel, right? This is my channel length. It's very conceptual, so concentrate please. Now I am saying when a certain condition is when is reached, the channel is completely gone at the drain end. I mean it's becoming 0. Charge Qi is becoming 0 over here. Let me draw it like this. Almost. Almost. Right? So can I say Qi over here? Qi. Its maximum where? At maximum at source end. Can I say that? Because this is source. And it is minimum at drain end. Yes or no? The source end is x equal to 0. Drain end is x equal to L. Agree? So here Qi is 0 and here Qi is maximum. Inversion charge is maximum at the source end, the minimum at the drain end. समझ में आया ये? Important point is inversion charge is varying with the channel length. And channel, varying according to the channel length. So at source end it is 0, at drain end it is source end it is maximum, at drain end it is 0. Agree to this?
Yes, sir.
हाँ. So this region of operation where the current becomes here at reaches the edge of saturation. This is edge of saturation point. And condition क्या है? VGS greater than VTO. VDS should be equal to VGS minus VTO. So यहाँ पे क्या होगा बताएं? यहाँ पे VGC 0 हो जाएगा. करेक्ट? N channel exist करने के लिए क्या होना चाहिए? VGC should be greater than or equal to 0. Yes or no? So यहाँ पे N channel exist करेगा. Actually greater than 0 नहीं, ग्रेटर देन 0 होना चाहिए. अगर इक्वल टू 0 है तो n चैनल विल डिसअपियर. नाउ इसके बाद व्हाट द स्टोरी इज, इफ आई अप्लाई अ हायर वैल्यू ऑफ VDS ग्रेटर देन 0.5 तो क्या होगा. इफ आई अप्लाई VDS ग्रेटर देन 0.5 तो व्हाट इज द स्टोरी. कैन एनीवन टेल मी व्हाट विल हैपन हियर. हेलो. एनीवन. Yeah, so let's see that condition over here. Okay, now listen carefully everyone, please. Let me redraw it. This is case number, actually हमारा case वो चला गया पीछे. We have defined yeah, VDS small, then we have got VDS 0.3 and 0.5. So ये देखो, this case was case number 4 where you have written this edge of saturation. So ये case क्या था, VGS greater than VTO and VDS was equal to VGS minus VTO, correct. VGS was 1.5, this is 1, so 0.5 था, ये case था, ये case 3. Now case 4, VGS is greater than VTO, okay, and VDS is greater than VGS minus VTO. मतलब क्या, if this is 1.5, if this is 1, this is 0.5, right. So VGS is greater than 0.5. So what will happen over here? What should happen over here? So that is what we will discuss. Okay. Yeah, everyone understood the condition? So this region of operation is called as saturation mode of operation. Saturation mode of operation. We say that the device is in the saturation mode of operation. Okay, so let me show you that document. So we'll directly go over here. So this is case number 5. Can you see this? We call it beyond saturation. So one more thing, as I go on increasing the value over here, like this, see, let me show you over here. As my channel becomes tapered and tapered, what happens to the depletion layer around it? Depletion layer को क्या होता है बताओ. So here depletion layer also increases towards this side, because यहाँ पे क्या हो रहा है पता है, यहाँ पे we are applying positive voltage, let's say 0.3, 0.5. So we are applying positive voltage to N plus junction, and negative voltage is P silicon, right? That is 0. So this PN junction is more forward bias, more reverse bias, sorry, than compared to this PN junction. Are you understanding? This is P silicon substrate, ये तो constant ही है, तो इसका depletion region will remain same. You tell me, if the reverse bias voltage increases, what happens to depletion layer in PN junction? Depletion layer increase होता है ना. So ये इसका, this depletion layer becomes like this. See, ये जो बनाया मैंने, don't forget depletion layer is present, huh? So depletion region becomes like this. Agree? So दो depletion region है, एक है gate and source के तरफ, gate and source, and other is drain. नहीं, one is source and the channel, other is gate, the drain and the channel. So drain and the channel over here is becoming, this PF junction is becoming more reverse bias. That's why this is tapered more. So that's why you see over here this depletion region is shown like this. Now let us see what will happen now. Let's say VGS is 1 volt. I hope this PDF is visible, right? VTO is 0.5, VDS is 0.8 now. So tell me, how will you calculate VGC gate to channel voltage at the drain end? कैसे calculate करोगे? VGS minus VTO minus VDS, correct? कितना हुआ ये? 0.5 minus 0.8. How much it is?
-0.3.
मतलब ये मेरा 0 का पॉइंट शिफ्ट हो गया. अगर ये -0.3 है, if here I am getting 0.3, let me maximize this. If here I am getting -0.3, that means my 0 का पॉइंट शिफ्ट हो गया. That means my pinch off point has shifted to the left hand side. That means the N channel is completely disappeared from the drain end and it's moving towards the source end. Yes or no? यहाँ पे 0.5 है तो यहाँ पे channel exist कर रहा है. Okay? यहाँ पे VGC is 0. QI is becoming 0. So this channel has shifted towards the away from the drain end. ये समझ में आया ये condition?
Yes, sir.
Okay. So QI is 0 at the drain end. So, but there will be definitely a channel at the source end. But no channel exists near the drain end. So, what happens next? So, the question is, when no channel exists near the drain end, what will happen to the electrons? Will they travel towards the drain or will the device conduct any current? ये बताओ, ये दो questions है. Now, channel disappear हो गया near the drain end. QI has become 0. So, what will happen to the electrons in the channel with those who are traveling towards the drain end? होगा क्या उनका? Will the device conduct? Will the electrons travel towards the drain? Answer. So मेरा ये pinch off point has moved away from the drain, right? Yes or no?
Right, sir.
Now tell me. So this mode of operation is called as beyond saturation. Now tell me what happens here. ये interesting चीज है. You want to understand this? ये समझ गया कि ये pinch off point has moved this side?
हाँ, sir.
Okay, now listen here very carefully. So in this case, what happens is I am only drawing the channel region. Rest all the things I am not drawing. I hope it will be clear. So this is N plus. This is N plus drain and source. This is my source. This is my drain. I know there will be an oxide layer above. This is oxide layer and उसके ऊपर metal layer. Gate. So this is my gate. Okay. So what has happened was VDS voltage मेरा कितना हो गया यहाँ पे 0.8. Okay. And VGS minus VTO कितना है 0.5. So due to that the channel has disappeared completely from the drain end. So मतलब ऐसे हो गया कुछ तो something this happened, right? So ये pinch off point moved हो गया यहाँ पे. This is pinch off point. So there are electrons coming now. Let me maximize this. There are electrons coming here. There are plenty of electrons in the N channel. To where all these electrons will go? This is N channel. और ये कभी होता है? What are the conditions? So the device is said to be in the saturation region. The device is said to be in the saturation region. Condition क्या है saturation region का? VGS greater than VTO and बोलो VDS greater than VGS minus VTO. Agree?
Yes, sir.
This is beyond saturation. Edge of saturation का क्या था? VDS equal to VGS minus VTO. ये है VDS greater than VGS minus VTO. ये conditions बहुत important है. So मतलब in my characteristics I have reached up till here. Let's say 0 to 0.1, 0.3, 0.5 की बात कर रहा हूँ. So it's like this. It continues to decrease. It continues to decrease. Reaches maximum value. तो इसके बाद क्या होना चाहिए? Ideally it should go down, right? ऐसे होना चाहिए ना? बराबर ना?
Yes, sir.
It should go down. But will the current become zero at beyond saturation point? That's the question. So will the current continue to remain constant? अगर ये constant जाएगा या zero गिरेगा? So what is the answer to that? Anyone knows it or anyone can guess what happens? We know what happens. We know from the curve that it will remain constant here like this. After this the current will remain constant. It will saturate. But why? Why current remains constant? That is what we have to answer. So anyone has any idea why it happens? Of course the depletion region, if we draw out over here, मेरे को depletion region इधर बनाना है. How will I make it? ऐसे है. ये मेरा depletion region बहुत ज़्यादा बढ़ जाता है. Here. So this PN junction is becoming, this is P channel, right? I hope you have not lost the track. This is P channel. तो ये PN junction is very reverse bias, heavily reverse bias. Okay? So we will answer why the current remains constant. Do you want to know it? The reason why it is constant? Can we start now with that? Okay, now concentrate, please concentrate for the last part. ये याद में रखो. Okay, so we want to understand why this pinch off point has shifted on this side. So this point, this region, we call this as a new L dash. So this is how will I draw it over here? ये मेरा L है. This is x equal to 0, right? This we call this L dash, new point, new pinch off point. Okay? Yes or no? ये देखो मैं बताता हूँ वापस. Again I draw it. So if this is n plus, this is n plus, and this channel has disappeared from here. So this point up till here, what do we call this? X equal to 0. This is L, and this is x equal to L dash. This is my new pinch off point. Okay. Actually, if in reality, if you see, this will be around, let's say, 180 nanometer, right? L is 180 nanometer. This point might be 179 nanometer. So very small distances there. Actually, we have drawn it very much bigger. It's a long channel, very much nearby. इधर से disappear हो जाता है. Okay, so this is x equal to L dash. This is the new pinch off point. Agree? Okay, so distance from traveled from year to year is very small. Whereas in this condition, the electric field, the depletion region will be like this. See, why this is like this? This is P silicon. बराबर है? This is P silicon. This is my substrate base. ये मेरा source है. ये मेरा drain है. And I know that I have an oxide layer. I'm not drawing that right now. Let me just show it once. This is my oxide layer. And top of it I have the gate. Okay, now depletion region क्यों increase हो रहा है? Because here I have told you P silicon source we are applying negative voltage, and here P silicon is like this only. So this is normal PN junction. If you form a normal PN junction also, there will be a depletion layer, but this PN junction here like this, I'm just showing it with an arrow. This is P silicon, this is N. We are constantly increasing. Earlier क्या था? Now we have made it 0.8. So we are applying positive voltage to N and negative voltage to P. So ये reverse bias हो गया ना? To reverse bias, as you increase, what happens? Depletion layer width increases, right? And something else happen. Electric field become very strong. Very strong. Okay. Yes. So carriers come near. I'll explain now. So this is what happens. So reverse bias increases, so electric field becomes very powerful. Why? Can you tell me what is the definition of an electric field formula? Electric field का formula क्या है? Voltage upon length, volt per centimeter. Yes or no? Hello?
Yes.
Oh, okay, fine. Now electrons. Now see, listen. This is very dicey. You can lose the track over here. Listen very carefully. So this is source. This is drain, and as I told you, this is very near towards the drain end. Drain end से it's away, but it's very much nearby also. यहाँ पे, somewhere around here. Okay, so these are N channel. These are this is my N channel. Okay, this is situation. And my depletion layer has increased to tremendously high value. मेरे source end में same है, but when I come near the drain end, the depletion region is very high, like this. This is my depletion layer. Why? Because here the electric field becomes very powerful. Electric field has become very powerful. Q, because right now these as I go on increasing my voltage VDS, my this PN junction, this is P silicon. So this PN junction will become more and more reverse bias. ये वाला. Okay. So what will happen is, see these electrons. There are electrons over here in this channel. Listen carefully. Electrons are traveling because you applied source and drain voltage, right? So electrons travel here, travel here, travel here, and they reach this point. Okay, तो इसके आगे क्या होगा? Lots of electrons are traveling and reach up till here. Now ये distance कितना है? L dash. ये distance कितना है? L. So how much is distance here? Delta L, L minus L dash, and that is very small. Let's say 1 nanometer or 2 nanometer. So right now, in this small area, the electrons have to travel a small distance to reach the drain region, right? So many of them are traveling. Have you seen this scenario that if there is two roads, road number A and road number B, okay, now if I have a vehicle over here, if I'm traveling on a vehicle and I maintain at a very high speed, if I'm traveling at a high speed, I can reach over here in spite of being a gap in between. Yes or no? Provided the gap should be less and the speed should be more. So let's say beyond 100 kilometer की speed होना चाहिए per hour. Then I can easily break this. I will not feel this. There is a hole only. I can easily reach on this side. ऐसे होता है ना बहुत बार in lot of हाँ. तो same reason यही है, इधर भी है. Now the second reason is the electrons have to travel a very small space. So जाएंगे कहाँ पे ये सारे electron? Have you seen when you have a soda bottle and you try to remove it and you try to shake it more and you try to remove the cap of it, there is a tremendous force coming out when they move out, right? So ये सारे के सारे electrons have become accelerated now. These accelerated electrons are accelerated by this very powerful electric field. ये electric field कहाँ से आया पता है? देखो. Now earlier the electric field EX was due to what? VDS. Yes or no? अरे yes or no? Now this electric field क्या कर रहा था? ये electric field was taking the electrons from the source to the channel to the drain region. अभी right now my channel is this much only now. Let's say delta L is my channel. इतना ये channel. So what has happened now? Electric field क्या हो गया? VDS पहले क्या था? First it was VDS upon L. अभी क्या बन गया? VDS upon delta L. Okay. So what has happened now? What has happened from here to here? VDS has increased and delta L is decreased. So what will happen to electric field? Will increase. Now how much it will increase, I'll let you know that also. Electric field becomes very very large. Delta L is becoming very very small. So electric field is becoming very powerful. So जो भी electrons इधर आ रहे हैं, they are accelerated towards this. So that means this example, same car का example. So as soon as it becomes near this, it's accelerating. So वही acceleration में all the electrons will reach towards the from the n channel towards the drain side with a constant speed. Now ये भी एक मतलब this also it's a known fact that there is something called as velocity saturation, drift velocity, the velocity with which the electrons will travel under the influence of electric field. So this electric field will reach the maximum value after reaching a certain point. So after you reach, let's say this velocity, I hope I have shown you the velocity saturation velocity 10⁷ na? In the labs, drift velocity almost like, okay, so it will reach a saturation point. After that this drift velocity won't increase, so this will be constant. So velocity of the carriers flowing won't increase more, okay, beyond this point. Are you understanding? This is a known fact. It's a known fact. You can check it out. Drift velocity versus electric field. So now the electric field goes on increasing, drift velocity won't increase. Okay, this is centimeter per second. So very very high drift velocity as these. So this will max out. So this is drift velocity of carriers. Velocity of carriers. मतलब now also electric field is volt per centimeter. But ये छोटे से region में electric field becomes in kilovolt per centimeter. Very very small because this is in micrometer na, so electric field becomes very very high value. So under the influence of this electric field, these electrons gets accelerated towards the drain region. और वो constant क्यों रहता है पता है? Why does the ID is constant? ना बता सकते हो ID constant क्यों है अभी? What is the reason? Because all these electrons attain a constant drift velocity. So ये constant हो जाता है ना यहाँ पे इसके बाद देखो After this point it has become constant. So the velocity with which the carriers travel from the n channel towards the drain terminal is constant. That's why ID is constant, or we can say ID saturates. ID saturates. Are you understanding? I don't know how much I was able to explain you all, but this is the real sense of what we have actually it happens. How does the electron does not go from this n channel to this area? So under the influence of very powerful electric field, which has becoming now VDS divided by delta L. Delta L is very small. Okay, so suddenly the electric field becomes very powerful. All the electrons coming near the n channel will attain that extra energy from the electric field, and they will be directed towards the uh, drain region, and all these electrons will attain a constant drift velocity. Because of that, the ID will remain saturated. So now the region of operation will be like this. See, this is VDS, this is ID. So पहले क्या था 0.1, right? It was constant, correct? Then it was 0.3, slope has changed. 0.5 में क्या हुआ? Slope has continues to decrease, right? So after this what will happen? 0.8 में अभी क्या होगा बताओ? It will remain almost constant and beyond. Even if you apply now 10 volt, it will be constant only. Okay, so this is what happens over here. So can we mark the regions over here now? So up till, can you tell me what is this region of operation? Beyond this, this is linear, correct? This region is edge of saturation, और ये वाला region क्या है? What is this region? Saturation. So this is the reason why the current continues to remain constant instead of falling down. ये normal tendency falling down था, but because of this phenomena which I have just explained right now, these carriers will continue to flow towards the drain terminal and constitute the constant current. Constant current क्यों? Because drift velocity of the carriers is constant. So this is the complete graph for one value of VGS. ये VGS equal to let's say 1 volt है. Are you understanding now? Hello? So this is how this characteristics comes. Output characteristics, one curve. I don't know whether how much you have followed, but this is what it is. That's why the ID saturates. ID saturates because drift velocity of the barriers is constant. So ID will saturate in the saturation. Actually ये saturation नहीं है, beyond saturation है. This is edge of saturation, this is saturation, and this is cutoff point. Cutoff. Agree everyone? Hello? Yeah. So this I have explained over here in words also. See this. Whatever I have explained, I have explained it over here in words. So these electrons will have to travel a smaller distance, delta L. So because of velocity saturation, your current remains constant in spite of no n channel being present. So we have a linear or triode region, edge of saturation, beyond saturation, cutoff for VGS less than VTO. So this is the characteristics which we have studied so far. Did you understand this now? Everyone? Please say yes or no. We have been, last 1 hour we are discussing this. It's little bit followed. I know it's a very basic thing. It's conceptual derivation, explanation for the MOSFET characteristics, but this is most important. Okay, everyone, we started with cutoff, then we moved on to linear, we moved on to edge of saturation, beyond saturation. You have understood little bit of it?
Yes, sir.
Okay, now let us write the conditions. So please write these conditions first. MOSFET in cutoff. What is the condition? Voltage के conditions बताओ. VGS less than VTO. Correct? Second is in linear mode or non-saturation mode. Condition बताओ. Here ID is 0. What are the conditions over here? VGS greater than VTO, and VDS is less than VGS minus VTO. Agree? Here ID flows. We call it ID linear. Then we have edge of saturation, or normally they call it as a velocity saturation. This point is called as velocity saturation or edge of saturation. ये कौन सा point है? VGS greater than VTO, VDS is equal to VGS minus VTO. I hope you are following. Here we call it ID lin flows. It reaches the maximum value. So ID reaches the maximum value at edge of saturation. Then we have fourth, beyond saturation. Okay, what are the conditions? VGS greater than VTO, VDS becomes greater than VGS minus VTO. If you are able to understand these things now, then fantastic. My job today is completed. If you are able to understand these conditions. Have you written the conditions? Hello? Yes, no, what?
Yes, sir.
Perfectly understood? Yeah?
Yes, sir.
Okay. Now I will explain you. Last part is pending, just 5 minutes, just spare it. I will explain why it is called as enhancement type MOSFET. N channel MOSFET you have understood, right? So whatever I have discussed, you can refer to the lecture. I have used both these documents together to explain you the output characteristics like this. Okay, if you have any doubt, you can refer to the recording. But these, conditions are very important to understand anything else. Now, next lecture onwards, we will derive all these things. We have to derive this. There is a proper derivation for ID linear. There is a proper derivation for ID sat. So we have to derive that. This comes in exam. So we have not touched that. We have touched only the conceptual working of MOSFET. Now, next thing. ये तो मैंने explain कर दिया खाली one curve. What if it is VGS 2 volt, VGS 3 volt? तो कैसे होगा फिर? What will happen? So let us explain that. Please listen carefully. So now I'll explain the last case, case number 6. So now we are increasing the value of VGS. VDS is constant, let's say. VDS is at 10 volt. Okay. 0 to 10 we are increasing. 10 volt hai. VGS is increasing. What will happen now? Tell me. What will happen if VGS increases? So now, if I have this, let's say, channel. So let's say VTO is how much? Let's say 1 volt. Okay, and ये 1.5 था, increased हो गया 2 volt में. Okay, this is n plus, just 5 minutes more. This is gate terminal. Okay, remember this, don't lose the track. Okay, now this is oxide layer, of course. This is my drain, this is my source and body terminal, and I am not showing. Now tell me what will happen. Channel to form hoga, right? So what will be there? Will there be any change in the VGS value? VGC value? Yes, VGC is VGS minus VTO. How much it is? बढ़ गया ना capacity? Earlier it was how much?
0.5.
Yeah, now it is storing more charges. Yes or no? तो मतलब चैनल कंडक्टिव ज़्यादा होगा, मतलब चैनल थोड़ा सा बिगर, मतलब यू कैन से इट विल बी मोर नंबर ऑफ QI. सो QI बढ़ जाएगा. पहले 0.5 था ना? Was it 0.5? Yes or no? Yes. So now it will have bigger space. So here VGC कितना होगा? यहाँ पे बताओ कितना होगा. चलो, VDS is, let's say, let's consider it as first case only 0.1 volt. तो बताओ यहाँ पे VGC कितना हो गया? यहाँ पे पॉजिटिव चार्जेस हो गए, यहाँ पे नेगेटिव चार्जेस हो गए. तो यहाँ पे VGC how much it will be at this end? VGC at source end, how much that will be? VDS is 0.1, So this will be VGS minus VTO. How much it will be? 1 volt. So यहाँ पे 1 volt होगा, right? VGC. How much will be here? So VGC at drain end कितना होगा value? VGS minus VTO minus VDS. How much will be this? 1 minus 0.9. देखो.
Yes.
Okay. So now if I draw this in comparison, ये देखो. Earlier क्या था? Earlier case I'm drawing this is 0.1, 0.3, 0.5, right? So here it was constant, here it was reducing, here it is got saturated. Yes or no? And then after that this curve was constant. अभी क्या होगा बताओ? अभी सेम चीज कैसे होगा? Now I'm going 0.5. So obviously this will be at a higher point, right?
Yes, sir.
This curve will be shifting higher at a higher point. अभी चलो बताओ एज ऑफ सैचुरेशन कभी रीच होगा? यहाँ पे 1 वोल्ट तक है ना. सो VDS कहाँ तक जा सकता है? Whenever VDS is 1 volt, then what will happen to VGC? 0 volt होगा, correct?
Yes, sir.
Okay. So this point has shifted up. ये 1 volt है यहाँ पे, तो somewhere around यहाँ पे हो जाएगा ये. Here. So this point will be, this slope will be higher. This slope will be even higher ऐसे, and this slope will be even higher. So then it will reach the maximum point. So ये same point it has moved up. तो ये वाला curve क्या था? This was VGS equal to 1.5. ये वाला कर्व कौन सा है? दिस इज VGS इक्वल टू 2 volt. Yes or no?
Yes.
So as I increase the value of VGS, what is happening? Current is becoming more because channel conductivity is increasing. That's why it's called as current is getting enhanced. Current is getting enhanced. Actually it enhances even further. Current is getting enhanced. So ID enhances with increase in VGS. Okay, now let's take the last case for today. Let's take that VGS को 3 volt कर दिया. 3 volt. Now tell me what will happen. 0.1 में here it will be how much? VTO is 1 volt only. Here it will be 2 volt, right? Here it will be 1.9. Yes or no?
Yes, sir.
And at what value of VDS will the channel disappear? 2 volt, right?
2 volts, sir.
हाँ, yeah. So 2 volt will be somewhere above point. So यहाँ पे और बढ़ेगा ये. This will be even more. So you will get a curve which is even higher. Actually beyond this, ऐसे मिलेगा. Agree?
Yes, sir.
So this is VGS equal to 3 volt. So that's why the channel, the current gets enhanced. So you agree this, if VGS increases, the channel conductivity increases. So whenever VGS increases, channel conductivity increases. Yeah, more space for the carriers to flow. Conductivity increases, and due to that ID enhances. So that's why it's called as NMOS, enhancement type MOSFET. Enhancement type MOSFET are normally off MOSFET. इसको बोलते हैं normally off MOSFETs. Because if I apply VGS is less than VTO, it is off. तो हम लोग off to on कर रहे हैं इसको. Normally off means off to on. You have to apply VDS also non-zero to turn it on. Okay, so that's why it's called as an enhancement type MOSFET. So that's why we get the characteristics which looks like this. See here. Now I'll draw all collectively together. So this is my, just a second. This is my output characteristics. I hope this will be there. Wait a second. Let me just open this document again. Just a second. Yeah, this is ID, this is VDS, and you get a curve which is like this, right? समझ गया ये? You get another curve which is like this. Sorry. And you get another curve which is okay. This will be constant. This will be the maximum points. So these points will go on shifting ahead, right? ये मैंने बोला था ना. So this curve is called as locus of these points. इसको क्या बोलते हैं बेटा curve को? This is called as VGS minus VTS locus. VGS minus VTO. ये change होता रहेगा ना? If VGS goes on increasing, बराबर ना? This is VGS equal to let's say 1.5, VGS equal to 1 volt, where VTO is 0.5, let's say. VGS equal to 2 volt. So this point will go on shifting ahead little bit. ये point थोड़ा सा आगे shift होगा. Here. Here. So if you join all these points, you will get a VGS minus VTO का locus. Here it will be like this. Okay, like this. So this is output characteristics of MOSFET. Now how will you get transfer characteristics? From here only, right? So this is ID versus VGS. So VGS equal to 1 volt will be here, 1.5 here, 2 volt here, 1.5, 2. So at 1 volt you will get some current which is here correspondingly. इसको mark करना है. Then second way, for 1.5 it will be over here, from 2 it will be over here, and at 0.5 beyond, this is VTO. So 0.5 तक ये बंद रहेगा curve. I mean it will be off, and after that it will go on increasing the current. ऐसे nearby this characteristics you will get. Will get this type of characteristics. Okay, and these are the points derived from the output characteristics. देखो ये वाले points. Okay, so this transfer characteristics is derived from output characteristics, so these need not be studied separately. Only thing is I can show off region over here. Wherever VGS is less than VTO, this is my cutoff mode. Actually cutoff mode इधर बताते नहीं हो ना. So this region is called as linear region, and this is saturation. So this is my transfer curve. Okay, so with this we have come to the end of the lecture. We have discussed together how the graph has built up for the output characteristics for the N channel enhancement type MOSFET, and how the derived transfer characteristics we can plot. Okay, and along with it we have also discussed very important conditions for voltages for various operating modes: cutoff, linear, edge of saturation, and beyond saturation. Alright, so yeah, that's all for today. I hope now MOSFET is clear to you, and we will proceed ahead to derive ID linear and ID sat in tomorrow's class. Okay, so that's all for today.